Welcome to lecture number 18. So in this lecture we will look at some examples of two-photon interference effects, and I'll also try to present some intuitive way of understanding two-photon interference. But first let's quickly look at what we did in lecture number 17, in which we rigorously derived two-photon interference and the coincidence count rate. So in lecture number 17 we considered a general two-photon interference experiment, two-photon interferometer, and we saw that a general two-photon interferometer can be represented like this in this unfolded two-photon path diagram, in which we have two alternative ways in which the down conversion can happen and the down converted photons can get to the detector. There are 6 length parameters involved in a general two-photon interferometer, in which we have two alternative pathways, and these 6 different length parameters then we combine to form these two length parameters delta L and delta L prime. We could also put together all the phases and come up with this quantity delta phi. Again, corresponding to this every length parameter, there we had the time quantity as well, which we represented by tau and so on. And with all these quantities, then we calculated the coincidence count rate, which was in terms of delta L and delta L prime, and we could also represent that in terms of the corresponding time quantity delta tau and delta tau prime. So the definition of delta tau and delta tau prime is pretty much the same. So this was derived very rigorously without any without reference to any particular two-photon interference, but this was done for a general two-photon interference. And we saw that if the pump and the signal idler fields have Gaussian spectra with frequency with delta omega p and delta omega, then these time averaged coherence functions gamma and gamma prime, they can assume this form. This was more for an illustration because gamma and gamma prime can take any functional form, but if the spectra are Gaussian, then of course gamma and gamma prime will have a Gaussian form. And for Gaussian, it's easy to define the width, and for such a Gaussian function, then we saw that this is the coherence width, coherence length corresponding to gamma, and similarly we can have this as the coherence length corresponding to the gamma prime. This coherence length is essentially the coherence length of the pump, while this coherence length, that is the coherence length, the width of the gamma prime function, this is calculated by the bandwidth, frequency bandwidth of the signal idler fields. And so for the two-photon interference experiment, we had two conditions for interference. One is that this delta L, for interference to happen, delta L has to be less than the coherence length of the pump, and delta L prime has to be always less than the this L coherence length of the signal idler field. Then we looked at the degenerate down conversion, in which the central frequency of the signal and that of the idler, that's the same, and if they have to be same, then they will have to be half the central frequency of the pump. So the difference of the two frequency or two vectors are 0, and if the amplitude in the two alternatives are also the same, then we and again for this situation, then we looked at the two special cases. First is when delta L prime is 0. This is in order to separate out the effect just due to delta L. So for this case, when delta L prime is 0, we see that the coincidence count rate, we see that as a function of delta L, there is interference, and that interference pattern decays down because of this coherence function. So in this sense, delta L plays the same role in two-photon interference as does the optical path length difference in the classical temporal interference or in one-photon interference. Then we look at the second case in which delta L is 0. This is in order to explicitly see how this two-photon interference depends on delta L prime. In this case, the coincidence count rate has this expression. Of course, there is no interference here, but if we change delta L prime, we pretty much see the profile of gamma prime. That is the time averaged, the coherence function, the degree of coherence. Again, delta L prime has no one photon analog or no classical analog. And then we also looked at that if we just look at the intensities rather than the coincidence of the two detectors, if we just look at the intensities, then the intensities at these individual detectors can also be can actually be written in terms of the coincidence count rate. This is pretty much the same as when we in the classical probability, when we write the individual probability in terms of the as a sum of the joint probabilities. So today we will see some examples of the very famous two-photon interference experiments in order to explain, in order to have much more intuitive understanding and feeling about this theory. So, as a first example of temporal two-photon interference, we will look at what's called the Hungermann effect. This was seen in 1987. This is a very famous famous two-photon interference effect. So, in this one, a pump photon gives down conversion, and these two photons are then mixed at a beam splitter. This is a beam splitter. So, of course, after falling onto the beam splitter, this photon can go this way, that way, or this way or that way. Now, if we look at the coincidence, so if we observe coincidence, the coincidence can happen in two different alternative ways. First is that the well, in this experiment, the effect that was seen is that when this beam splitter is moved up and down, the coincidence count rate here actually changes, and when this beam splitter is in the balanced position, that means when this x is 0, then there was no coincidence over here. Now we have these two photons coming in here, and then we observe no coincidence when this beam splitter is in the balanced position. What that means is that if there are no coincidence, that means there is no event when one photon goes this way, one photon goes this way. If there is no coincidence, that means both the photons either go this way or they go that way. So when we in the experiments, when we look at the coincidence count rate as a function of x, then we see that at x equal to 0 there is no coincidence. So this means photon, this had the interpretation that when we combine two entangled photons at beam splitter in the balanced position, both these photons get bunched and then they go either in this direction or in that direction. So this was the effect seen. So how do you explain this? So we explain this by the theory we have. This is, so here if we see coincidence, that means there could be two possible ways in which the coincidence can happen. First is that both these photons get reflected from the beam splitter, or both these photons get transmitted through these through this beam splitter, and in each case we will get coincidence. Of course, when one gets reflected and another one transmitted, we will not have any coincidence, and so for our coincidence count rate, that will not contribute. So we will just look at these two alternative pathways. If we put this in the unfolded two-photon path diagram manner, then we see we can write it like this. I mean, of course, we see that when now the beam splitter is in the balanced position, then this is just exactly, these two are exactly equal, and of course this, when things are transmitted, the beam splitter displacement does not change the path length. So that's why there's only change here, because when we push the beam splitter up or down, the one that is going reflected, that has a change in the path length, and that path length we can show just the simple geometry that path length is 2x cosine theta. Of course 2x cosine theta will be for this one as well, so total of 4x cosine theta. And then there are these phase differences incurred because of the reflections. There is a reflection from the mirror, then there is a reflection from the beam splitter. Beam splitter gives a pi by 2 phase, mirror gives a pi. So there is a 3 pi by 2, 3 pi by 2 here. In this case, there is no reflection from the beam splitter, just a transmission, and so there is just phase pi and phase pi over here. So in this case, if we calculate this is our general coincidence count rate, and so we need to calculate delta L prime and delta phi. So delta L in this case is essentially 0, because this central the mean position here and the mean position here, the difference is not changing, the delta L is 0. Delta L prime in this case is 4x cosine theta, delta phi is pi. So if you put in these quantities over here, we see that the coincidence count rate is 1 minus gamma prime 4x cosine theta. Of course, this cosine theta is a fixed number, and then we are just changing the x. So, as a function of x, we just recover the profile of gamma prime, and since there is a minus, we get a null here. So, this is the way we can explain this effect. But then there was this initial interpretation when this experiment was done. There was this initial interpretation that since we see a 0 in the coincidence, this means at this location the two photons that arrive together, they actually get bunched and they either go this way or that way. So there was a kind of challenge to this bunching interpretation, and then there was another experiment done after almost 9 years, and this was called postponed compensation experiment. So this experiment, it was essentially tried to establish that even when there is a delay in the arrival of the two photons at the beam splitter, we can have very similar results. That means we can still observe a 0 in the coincidence count rate. So this is how this experiment was done. In this experiment, it was made that the polarizations of the signal idler photons were different. For example, this was Y polarized and this was X polarized, and in the Y polarized photon, there was a delay D that was introduced, and then these photons were then mixed at the beam splitter, and then after the beam splitter, twice the delay was introduced in one of the polarization only. So the delay was introduced in such a manner that if it is a X polarized light photon coming in, then it will see a delay of 2D, but if it's a Y polarized photon coming in, it won't see any delay. So for this experiment, if we observe any coincidence, then that can happen in two different alternative ways. In first alternative, both the photons are getting transmitted. So that's the Y polarized, that's the X polarized, and since they get transmitted, we have Y here, and the X goes like this, but since X polarized light will see a delay of 2D, so that's why we have picture like this. In the second alternative, both the photons, they have to be reflected in order to give us coincidence. Now in this case, Y, since it gets reflected, so it goes in this direction, but it won't see any delay. The X photon gets reflected, it goes directly here. So these are the two alternative pathways by which we can actually see coincidence. So the interference is then the interference of these two alternatives, and in order to kind of see that, let's we put this in this unfolded diagram manner. So here all these the phases are pretty much the same as what we had for the Hungermann. In this first alternative, we see that so here whenever we have this two photon diagram, we always look at or calculate it from the detector's perspective. So whatever comes here is whatever comes at the signal detector is actually the signal photon. Here we see that the photon that starts from here, the photon that starts from here gets to the signal detector in this alternative, and the photon that starts from here gets to the signal detector in the second alternative. But from the detector's perspective, we call it signal, we call it the signal photon whichever gets to the detector. So in this alternative, this one is the signal photon. In this alternative, this one is the signal photon, and that's how we draw it. Okay, so these are the two detectors in the first alternative. That's how the two photons reach the two detector, and since this is a possibility where both photons are transmitting, so a change in the beam splitter position is not going to introduce any path length changes. So this remains, the path length remains exactly the same. It doesn't depend on the beam splitter displacements. So the difference between the two path length, that means the signal idler, is D. Now in the second case, in the second alternative, let's say when we are at the balance position, let's it will be helpful if you can draw. Let's in the balance position, what we have is that this goes only up to this point, and the signal, and this one goes up to this point, so that the difference is again D. So this one has an extra d, and this one is d less. So that's the length traveled by the signal photon. This is the length traveled by the idler photon, and the difference is d. So in the balance position, in the first alternative, the difference of signal idler is d. In the second alternative, also the difference of the signal idler is d. And from the balance position, when we start moving this beam splitter, then of course we introduce we increase the path length of signal photon by 2x cosine theta, and we reduce the path length of the idler photon in second alternative by 2x cosine theta by the same amount. So in this case, of course, this is our coincidence count rate, and for evaluating this, we need to have delta L prime and delta phi. Now delta L in this case, is the separation between this midpoint and that midpoint, and which is just d. Delta L prime is 4x cosine theta, because this difference and this difference are equal, so that their difference is 0. So in the balance position, delta L prime is 0. It's only when we introduce x we get delta L prime, and that's 4x cosine theta, and delta phi is just pi. So this is pretty much same as the Hungermann effect we did in the last example, except that delta L in the other case was 0, and now it is d. So if we just substitute these values in here, the coincidence count rate is given by this expression. We have gamma d, gamma prime 4x cosine theta cosine k naught d. Of course, this is a fixed quantity. Gamma d is also a fixed quantity, and if we assume that d is much smaller than the coherence length of the pump, then this is pretty much equal to 1. And this is just a fixed quantity, so as a function of x or 4x cosine theta, what we see is just the profile of gamma prime, and hence we see a 0 in the coincidence count rate. Now this experiment had a profound effect as far as interpreting the Hungermann effect was concerned, because it was clearly shown in this experiment that even when the photons arrived not simultaneously, there still was a 0 in the coincidence. Of course, if the photons are not arriving simultaneously, then we cannot have this usual bunching interpretation that either photons are coming together, then they bunch and go in this direction or in that direction. So we cannot have that interpretation over here, because the photons are not even not arriving simultaneously at the beam splitter, hence they cannot have any interaction between them. So this is again just a two-photon interference effect, and from that perspective, the first one was at delta L equal to 0, and the second one was at delta L prime, delta L equal to d. So the point here is that all this two-photon interference experiment can be described in terms of delta L prime and delta L, just as the one-photon or classical interference we can describe in terms of delta L, that is the optical path length difference. Okay, so let's look at one more experiment. This was even more mind-boggling. This was in 1991. It's called induced coherence experiment. In this experiment, there was a laser. That laser is split into two. There's a two different down conversion crystal. So the photon can get down converted either. I mean, a pump photon starting from here, it can either go this way or go that way. When it goes this way, it can get down converted over there, and the two down converted photons can reach the detector like this. So signal goes like this, and idler can go like that. The pump photon can actually go in this direction and then get down converted, and the down converted photons can then go like this and like that to the two detectors. So if we want to calculate the coincidence between a detector A and B, then the two ways in which we can get coincidence between A and B are these two alternative pathways. Of course, here I must mention that down conversion happens either in this one or in that one. So a pump photon either gets down converted in this way, or it gets down converted in this manner. Both of them do not happen together. Of course, there is a finite probability of that happening as well, but in that case we will get a 4-photon, that means 2 there, 2 here and 2 here, and that will be a 4-photon effect, and right now we are not discussing that. So we are only discussing those cases when the down conversion happens either here or over there. So in that case, we can represent the two alternatives that lead to coincidence detection in this manner, and then it's easy to, this is our coincidence count rate, and in this case we can actually show the delta L in this case is x cosine theta, delta L prime is twice x cosine theta, delta phi is pi. So in all these two photon interference experiments, one simply needs to calculate delta L prime and delta phi, put in here, and that is the effect one would see. So that's what we have over here. And if we just calculate RAB, that these are the two detectors, so that's 1 minus gamma prime twice x cosine theta, gamma x cosine theta, and cosine k naught x cosine theta. So this x is basically the beam splitter displacement. So as a function of this beam splitter displacement, one would see interference because this cosine term in the coincidence count rate. Okay, so this was not the surprising result of this experiment. The surprising result was that one actually sees interference here as well. And before we do that, let's first, and this fact was surprising because for observing one photon interference, I mean, if you look at the intensity here, the two alternative ways in which we can have intensity or one photon detection at this detector one is like this: the signal photon can get to the detector like this, or the signal photon can get to the detector like this. So these are the two ways in which we can see a single photon detection over there. But we see that the path length difference between this and that is of the order of 15 centimeters or so in this experiment. But we know that the coherence length of these photons are of the order of hundreds of microns. So when the coherence lengths are of the order of hundreds of micron, but then the path length difference is 15 centimeters. So how can there be an interference? But it was actually seen experimentally that there was interference, and that was quite mind-boggling at that time. So this is explained by the one photon count rate, and here we had that the individual count rate or intensity at a given detector can be represented in terms of the coincidences. So in this case, if we detect a photon at detector A, then what are the possible places or location where the entangled photon can go to? So if the signal comes here, the corresponding outlet is this, it has to go there. Or if you look at this down conversion signal comes here, the corresponding idler can only go here. So if we detect a photon here, its corresponding idler or the corresponding entangled photon can only go to the detector DB. So in this case, RA is just equal to RAB. But if we look at the intensity at the detector DB, if we get a photon here, then what are the places the other photon can go to? So if we detect an idler here, for example, from this alternative, its signal can go here, but it can also go there, although there is no detector here, but it can definitely go there. Or if we detect an idler in this way, then its signal can go here as well as it can go over there. So for a photon detected at dB, its corresponding entangled photon can go either to dA or dC, even if the detector is not there, and that's why the singles count rate at RB is equal to RAB and RCB. So let's we already have calculated RAB here. Let's calculate RCB. So RCB is now the coincidence between detector C and B. It is pretty much same as this one. We can, if we just calculate, we see that the delta L in this case is minus x cosine theta, delta L prime is minus twice x cosine theta, and delta phi is 0, and delta phi was pi here. As a result, the coincidence count rate between C and B is C 1 plus gamma prime twice x cosine theta, gamma x cosine theta, and twice cosine k naught x cosine theta. So here we see this expression and this expression, these two are pretty much the same except for the sign here. This is minus over here and this is plus over there. So now if we calculate RA is simply RAB, so this is what we see, and since here we see an interference, we will actually see interference in RA as well. But for RB, this is a sum of this coincidence and that coincidence, and we put them together, we just have twice C. There is no interference, and this is actually what we see in the experiments as well. So if we just look at the from one photon perspective, we just cannot explain this interference over here, because the path length difference between this and that, these are the one photon alternatives, that is 15 centimeters, and the coherence length of the photon is hundreds of microns. So we just cannot explain that interference. But the interference in the singles interference, or interference the one photon counted here, is actually not due to singles interference or one particle interference. This is still due to two particle interference, and when we express it in that manner, we can actually explain it. So this is how it works. Okay, so so far we have done a very rigorous analysis of two photon interference experiments. We also did two examples. Again, mathematically, rigorously, we did everything. So, but now I just want to have some intuitive feeling of how two photon interference actually works. So before that, let's just look at the way we intuitively understand one photon interference, and that is always by this very famous statement by Dirac, that a photon interferes with itself. So let's take this example of Michel's interferometer. In interferometer, we see, we have a photon starting with a laser and gets to the detector. It can go to the detector in two different ways. One is by this, another one is by that. We can write these two in the unfolded manner, and their path length difference is delta L. And we have seen that the intensity of the detector then can be written as 1 plus gamma, that is a coherence function delta L, and cosine k naught delta L. So if we change delta L, we see interference. Again, that interference goes away within the width of this coherence function. So necessary condition for coherence here is delta L has to be less than the L coherence, that is the coherence length of the field. So the intuitive way that we understand here is that one associates a wave packet with the photon in each alternative. This wave packet is not the intensity packet. This is basically the coherence packet, the size of the coherence function. And in fact, in the quantum theory, we have photon either here or here, so it's pretty much the wave function. So this is not the wave packet in the sense of an intensity packet. This is just the coherence packet. So we can imagine a photon or the wave function carrying a coherence wave packet with it in alternative 1, and again similar size coherence wave packet in alternative 2. And the interference happens when we change delta L. So when we change delta L, these two packets overlap, and if the overlap is perfect, we see perfect visibility interference, and if when the overlap diminishes, we see interference with lesser visibility, or after a while it actually becomes 0. So this is our intuitive understanding of one particle interference. So as we increase, for example, this mirror, that increases delta L, and as we increase delta L, the overlap between the coherence packets in the two alternatives, they change. When delta L is 0, the overlap is perfect and we see maximum visibility fringes. When the overlap is a minimum, then we see visibility, the interference with much lesser visibility, and of course the interference goes away within this length scale, which is the coherence length of the field. So this is how we understand one particle interference, and we say that this alternative interferes with this alternative, and that is the sense in which one means a photon interferes with itself. And as long as these two alternatives are coherent, one sees interference, and once that goes away, one doesn't see interference, and the condition for coherence is this. So this is our understanding of one particle interference. Now the question is, can we have a very similar interpretation or similar understanding of two particle interference? So we have already seen that for two particle, we have as a source a parametric down conversion. So we have one photon that breaks up into two. Now these individual photons, we've seen that they have a much wider frequency bandwidth, and then correspondingly they have a coherence length, the individual ones. Now in addition, we can think of these two photons as having a much bigger coherence packet, and that is given by this LP coherence, the size. Of course, the after down conversion, the pump photon is no longer there. I mean, we represent it like this because most of the photons are not down converted in an experimental setup, but the two photons that are produced, that was from a photon that is no longer here. So after down conversion, the pump photon is not here. We only have these two photons, but we can imagine that these two photons that have these individual coherence lengths are surrounded by this bigger coherence packet, size of which is decided by or given by the coherence length of the pump photon. Now, let me also remind that the coherence length of the pump or the laser in typical laboratory setup is about 10 centimeter or so, and the signal idler fields can have the coherence length of 100 microns or so. So with these numbers, let's see if we can have an intuitive understanding of two-photon interference in this kind of coherence packet representation. So again, in the one photon case, we had a single coherence packet. In the two photon case, we have the smaller coherence packet associated with individual photons, and then we have an overall much larger wave packet or the coherence packet associated with the two photon state itself. Again, these two photons need not always be together, they can actually go a little non-collinear, but this wave packet the coherence packet representation still remains intact. So let's go very quickly through the two photon interference expression we derived. So this is this we took as the generic two photon interference experiment. These were the two alternative ways in which we can have coincidence detection, and then we use these length parameters for defining delta L, which we can call two photon path length difference. We define also delta L prime, that we can call two photon path asymmetry length difference, and we put all these phases together to define delta phi, and this was the expression for two photon coincidence count rate that we derived, and correspondingly we had two necessary conditions for two photon interference. So now we want to have a coherence packet kind of a representation for these interference that we see in this coincidence count rate. So first we will look at the effect just due to delta L, and then effect just due to delta L prime. So again, we will use this experimental setup itself, and in this experimental setup we will change these mirror positions such that delta L prime remains 0. So in this setup we have these two alternative pathways, and let's imagine that in the balance position all these distances are equal. That means the distance of the pump mirror, signal island pump mirrors are equal. Now from that position, if we start moving this idler and the signal mirrors by amount x in the same direction, then we can actually just show through this two photon path diagram that delta L in this case is twice x, delta L prime is 0, no asymmetry, and delta phi is pi. And so in this case the coincidence counter is just 1 minus gamma twice x cosine k naught twice x. So here I am representing this experimental situation in terms of the coherence packet. So then this is alternative 1. We have these tiny wave packets, tiny coherence packet corresponding to signal idler, and that's the bigger one corresponding to the pump coherence length, and same in alternative 2. And now we will change x, that is the mirror position, and see how this overlap actually works. Now since for in the two photon we have two separate coherence condition, first one is with respect to delta L, and so that has to be in terms of the overlap of these the bigger coherence packet, and then the delta L prime has to be in terms of the overlap of the smaller coherence packets. Again here delta L prime is 0, so we will not expect the smaller coherence packets will have perfect overlap, and since we are changing delta L only, we will expect only these wave packets overlap to change. So let's increase x in this case. That means we are moving these mirrors from the balanced position in the same direction by the same amount. In this case, there is no asymmetry introduced between the two individual packets, and as a result delta L prime remains 0, but delta L changes, and that's why this overlap between this bigger coherence packet is actually changing. And so what we have is perfect interference when there is perfect overlap, and then the visibility of interference goes down when the overlap is not so perfect. And of course, the entire interference pattern interference gets washed out within this length parameter, which is the coherence length of the pump. So we see this is pretty much the same intuition that we have for one photon interference, and in this sense we call it that a two photon interferes with itself. The only difference from one photon is that here in one photon we have one coherence condition, but now we have two separate coherence conditions. Let's look at another experimental situation where we have delta L as 0, and this we can achieve by making sure that we from the balanced position we move these two mirrors by the same amount but in opposite direction. So then we can show that if this is achieved, then we have delta L as 0 because the midpoints remain wherever they are. Delta L prime becomes 4x, delta phi remains minus pi, and then the coincidence count rate in this case 1 minus gamma prime 4x. So no interference in this case. So since delta L is 0, this overlap of the bigger coherence packet that remains intact. The overlap of this thing, the smaller coherence packets, they will change, and as a result the interference will take place. So if we change this x now, that means move signal idler mirror by the same amount in the opposite direction, then we are keeping delta L fixed at 0 and we change delta L prime. And as a result, we keep, although we keep this coherence condition fixed, this coherence condition is changing, and when the overlap is perfect, we see nice interference in terms of seeing this the profile of the coherence function. But when the overlap is not perfect, then I mean the visibility interference goes down to the extent in the same proportion as the overlap. So again, in a general interference scenario, we can have both delta L and delta L prime changing, and in that case it will be the effect of the overlap of both these different types of wave packets. So that is one intuitive way one can understand two-photon interference, and what one means by saying that a two-photon interferes with itself. For today's lecture, we will stop here. Thank you.